You can use this study guide if you want as one side of one page for Friday. I put this together from a book that's called Writing to Learn Mathematics, and I use this as a discussion forum on my online 107 class. But you can use it as a study aid, and if you want to put notes on the back, that's fine. Whatever you want to do, it's up to you. Also, check out the Moodle site because it has a link on our Moodle site to the video solutions to the study guide that's in your packet. You have a study guide at the end of class 9 for the test. So the solutions to that are on Moodle. You might recognize it's a different voice because it was Ian Winokur put those solutions up for us when we were teaching a couple of years ago, so there's no sense in duplicating efforts here. We all can use it regardless of who's doing the video. So if you recognize a different voice, projects will be handed back Friday. Please get here early on Friday if you think you're going to need any more than the allotted hour and 10 minutes. If you tend to be a student that traditionally has run out of time, or you have some kind of accommodation for more time, then come at 10 or 10 past or 10:15 so that you're not nervous about the time. I will collect, 8 o'clock or 8:10 or 8:15. I will collect it right at 10. So if you came in at 8, you'd have a full 2 hours. If you came in 8:30, an hour and a half, you can do the math. So let's do class 9. Class 9, as I mentioned, will not be on the exam, and that's why on this study sheet you notice on the study aid, it has two things, not for test 1, not for test 1. But you could write beside that, will be on test 2. So if you make a note there, you could complete, a section like that to study for your test 2. That's way off in the future. That's not to April 2nd, assuming we have no more snow days. Okay, so let's start us off here, Tony.
In our previous class, we looked at how to solve polynomial equations. This is going to continue our work, special category equations that are quadratic in form.
I should say that are quadratic in form.
We know from our work in section 1.5 the general form of a quadratic equation: ax squared plus bx plus c equals 0, where a is not equal to 0. So the question of the hour is what do equations that are quadratic in form look like? Examine the equations to see if you can find patterns.
Okay, so what I've done is I've put the quadratic equations on the right side and equations, believe it or not, that are exactly the same almost on the left side. And all I want you to do is say, look at the look at the quadratic equations on the right side and then compare them to the ones that are quadratic in form on the left side and see if you recognize any patterns. And just take a couple minutes with your group and write down whatever you notice, and we'll talk about it in a minute. Please. Anybody feeling brave today to want to say to the whole class, oh, we're so scary, what you wrote down? Colton. Right. Okay, so the quadratics, as we know, we call that their second degree equations, right? Because the highest power you see is 2. They're all set equal to 0. Same with the ones on the left side. However, the ones on the left side don't have highest degree of 2, except for this one. The middle one has a highest degree of 2, right? The highest power you see here is 2. So, yep, these ones down here have fractions. So what pattern is going on here that helps us to say that these are quadratic in form? Can anybody see a pattern here that holds true for these three on the left-hand side? It's the same pattern. Ed? The exponents are in descending order. Yep, that's a key idea. But there's something even more specific about the exponents that appear here, 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 and here, other than that they're in descending order. So what are the powers of each term here? What would be the, excuse me, the degree of each term here? Degree of each term. A term is this thing right here, anything that's on the other side of an addition and subtraction. So what would be the what would be the degree of that first term that I've got in a box there? What would be the degree? 2, and then the next one, 1, and then it goes to 0, right? All right, what about the next one down, this one? 2, 1, 0. 2, 1, 0. Let's take a look at the degree of each term here, degree of each term. So what about this one? What would be the degree of each one of these terms in order? 4, 2, 0. What about this one? 2, 1, 0. So that's exactly the same as all of the quadratics on the right side. And what about this one here? What's that say? Can you see what that is? That's actually should be 2/3 and 1/3. Okay, so what would be the degree of the first term here? 2/3, 1/3, and 0. Okay, they all end with a constant number. That's why you have degree 0. Any constant has degree 0. So what pattern do you notice here? Well, you say, and it's the same pattern here. You can't just say that they simply descend, because if I had something like this, x to the 4th minus 10x cubed plus 9, it would not be quadratic in form. So maybe it would help you for me to tell you something that's not quadratic. So in other words, if I had this, that's not quadratic in form. So there's another key idea here that's going on that makes these quadratic in form, and it has something to do with the relationship between the degrees of your exponents. They're multiples of 2, 1, and 0, exactly. Notice, in a quadratic, the degree of your middle term, 1, is half, right? It's half of the highest degree. 1 is half of 2. Or 2 is twice the degree of the middle term, however you want to look at it. Look at this. Has the same relationship. If I double this, 2, 1, 0, what do I get? 4, 2, 0. This is exactly the same already. This is already quadratic. This is really a quadratic equation. And this one, it doesn't matter. 1/3 and 2/3 have that 2 to 1 relationship. If you multiply 1/3 by 2, you get 2/3. Or if you take 2/3 and cut it in half, you get 1/3. So anytime you notice a polynomial equation where the degree of your terms have this 2 to 1 relationship, and then your 0, your constant, then it's quadratic in form. Right? So let's see how we deal with these. How do we approach these? Well, there's a little strategy you can use, and this idea is used a lot in mathematics. When you go and take calculus next semester, or pre-calc and then regular calculus, you're going to hear about this idea called substitution, U substitution. In particular, you'll run across this in your second semester calculus course quite a bit. So once you recognize, and that's the key, here's an equation and you say, oh, that's one of those equations that looks quadratic because the degree of my first term is twice the degree of my second term. 4 is twice 2. And my last term is constant. All right. So once you notice that, then you say, okay, this is going to look and be solved something like a quadratic equation, so you know where to go in your little compartments that you've stored in your brain. So the first thing you want to notice here is what the degree of your original equation is, and what's the degree of this original equation? What's the degree? 4th degree, because the 4 is the highest exponent. So how many potential solutions could you have to this equation? How many? 4. So you can have up to 4 solutions. Okay, up to 4. Well, you'll always have 4. It's just that sometimes you might have remember we ran into this last time with the polynomial equations. You might have three distinct, and you count one of them twice. If it's like x squared equals 0, you count that 0 twice. So there's really 4 solutions, but you may not have 4 different solutions. All right, so here's a little key. Since x to the 4th, since this term is the square of that term, since the first term, x to the 4th, is the square of x squared, we use this strategy where we use this u substitution, okay? We let u equal x squared. So notice we can write this equation over again, okay, by writing, instead of x to the 4th, we can call it our middle term, which is x squared squared. And then our middle term is x squared. So you see how this x squared appears twice. All right, now what you do is you let u, you could use any letter in the world you want, but u tends to be the famous one that's used throughout calculus a lot. They call it u substitution. So you let u equal x squared. So if I let u equal x squared, then my first term is going to look like this. X to the 4th will be u squared, because x to the 4th is x squared squared. And I'm calling u x squared. So all I'm doing is substituting u for x squared. So my next term would be minus 10u plus 9 equals 0. So once you replace the x squared with u, now look at what you're looking at. You're now looking at a quadratic equation that you know how to solve. Except for now, your quadratic equation you'll be solving will be solved in terms of u. And you've got to go back at the end and make it in terms of x. So right now you look at that and you say, oh, no problem. I can factor that. U minus 9 times u minus 1 equals 0. I'm not going to be all wigged out by those x to the 4th powers and all that. And now you use your zero product principle. You set each of the factors equal to 0. And you solve. U equals 9 and u equals 1. So just what you were doing the whole time you were solving quadratic equations. That's why they're called quadratic in form. They're not quadratic because it's a 4th degree equation when you start. But they have that pattern that Lee mentioned. Okay. So why aren't we done? Why don't we just circle, Tony?
Because you have to, u is x squared.
Right, u is x squared. Remember, our original equation, you're going to be told solve for x. Well, this isn't solve for x, it's solve for u. So now you come back and say, hey, what does u equal? U equals x squared. So you replace each of these u's with x squared, and then you finish. And so you don't run into your little mistakes that when you have x squared equals a constant, remember, how many solutions? Circle that 2 to remind you. And this is where I would suggest that you set both of these equal to 0 and factor so you don't forget that you have 2 different answers. X squared minus 9 is x plus 3. X minus 3 equals 0. X minus 1 is x plus 1. X minus 1 equals 0 because those are both difference of squares. And now no way will you forget that you have 2 different answers for each of these. So notice you have 4 different answers. Your original equation was the 4th degree. And when you list your answers in your solution set on my math lab, you always start with your smallest solution and work your way up. So it's sort of like a little thing you do visually to help you recognize how to solve the equation. Now, let me just say to you, you can forget this whole u substitution if you want. Some of you may be capable with the original equation. If you recognize that when you factor your original quadratics, you get 2 factors. Like if this was an original quadratic like this was just an original quadratic, you factor this into 2 binomials where each one of these factors, each factor is linear because they have degree 1, okay? You can still use the same exact techniques on this that you used here. The only difference is when you get your two factors, they're going to both be quadratic factors. You can still say what factors of 9 add up to 10, 9 and 1. And now when you factor, instead of it being x and x as your first term, it's x squared. So you can just do this if you don't like the u substitution. And then you set each of these equal to 0, and we're right back to where we started a minute ago, getting our two different answers for each factor. Okay, so just because it's in this form doesn't mean you can't factor it like you traditionally factor it. Okay, so that's quadratic in form, right? And you'll have a few of those on homework. This homework will not be due until Monday, the 24th, since you have an exam on Friday. Any questions on anything we've done here before we move on? Because if it will just continue to be the same question because we're going to do a couple of these. Any questions at all? All right, let's take a look at the next one. So this one, if you were left to your own devices on this one, you might be tempted to square this first term out and then use your distributive property and do it out the long way, which is okay. But part of what I want you to recognize here is the pattern that you have 2, 1, 0, right? You have the pattern of it being quadratic. So if we were going to use this u substitution, we're used to seeing like one little baby variable squared, right, as the first term. So what could you let u be so that that stuff in parentheses doesn't mess with your visual field? What would you let u be here so that would be a lot easier to look at and it would really look like a quadratic equation? Okay, x plus 3. Okay, thank you for Caitlin. All right, so if you let u equal x plus 3, then everywhere you see an x plus 3, you just replace it with the letter u. And then it's a lot easier on your visual sort of brain to look at that and say, oh yeah, that's definitely a quadratic equation. It might be hard to recognize this, but once you do that, now you just go to town and you say, okay, what factors of 18, because I have a subtraction there, I use the term differ by 7. So what factors of 18 differ by 7? Not those differ by 17. How about 9 and 2? Yeah, and because your middle term is positive, you're going to have a plus and a minus. So you can easily factor this. And you set each factor equal to 0, and then you set each factor equal to 0, and you solve for each in terms of u. But you're not done because we're not solving the original equation for u, we're solving it for x. This is where you go back and you substitute in, what does u equal? U equals x plus 3. Since u equals x plus 3, you come back here and you replace u with x plus 3. And now you solve the equation for x, which is just a linear equation. You subtract 3 from both sides, you get negative 12. And on this one, you get negative 1. And now, because I'm a good doobie, I'm always going to check my answers because I get nervous when I start doing all these crazy things to equations. I go back to my original equation and I throw in negative 12 and I see if the left side equals the right side. So let's see. Negative 12 plus 3 is negative 9. Negative 9 squared is 81. Negative 12 plus 3 is negative 9 times 7 is negative 63 minus 18. 0 equals 0. That checks. Then I do the other one. Negative 1 plus 3 square minus 7 times negative 1 plus 3 minus 18 equals 0. Negative 1 plus 3 is 2. 2 squared is 4. Negative 4 minus 14 minus 18 equals 0. Does that work? Does that work? Nope. So the only solution here is negative 12. All right, so there's just one solution. All right, so you always got to check your work when you're done. All right. right, let's see what, oh, does anybody see a mistake I made? No, nobody sees my mistake? Well, what about this? Is that right? What's my original equation? Plus 7, right? So that should be a plus, that should be a plus. So I get 18 minus 18, 0 equals 0. So both of them are okay. All right. Okay, so that's quadratic in form. I want to skip this one for now and come back if we have time at the end. So we got started a little late today. I'll come back to this. It's a you try anyway, so you can try at the end of the class. But let's start the next type of equation, which is really the last equation you'll be responsible for in terms of this whole series of equations that you see in section 1.6. So let's use our graphing calculator to solve the absolute value of x equals 3. By using the technique we've talked about, we're going to let everything on the left side be y1 and everything on the right side, which is just the constant 3, be 3. And let's copy our graph onto our paper here. So let's see what we get. Oh, I better get that camera up and ready because otherwise I won't be able to copy it. Let's see if I've learned it the right way. So let's see. So we're going to let y1 be absolute value of x, and you say, how do I put absolute value in? Does anybody know? All right, there's two ways. You can go to your math button right here, your math button, and go over to num, and the first thing you see there is absolute. So you just hit that, and you throw an x in the middle, and you can put the parenthesis or not, it doesn't matter. And then you come down here and you do 3, and now you say standard window, which is 6, and it will graph. And there's the absolute value of x, and there's the y1 is the absolute value of x, and y2 is your constant line, y equals 3, which is just a horizontal line. So where are our solutions? How would I find our solutions when I look at a picture like this? Where are the solutions? What are the solutions to this equation? How do you find them? They're the intersection points, right? You're trying to find the x that's common to both of these. So it's going to be the intersection points. So let's copy this picture. Okay, and put it down because you'll be doing something like this probably on your test. So you might as well review this. So here we go. There's the graph. So we're looking for the x coordinates of the intersection points because we're solving for x. At this point, we know what y is. What is the y value for each of these? What is the y value? 3, because look, you've just drawn the line y2 equals 3. So we already know the y value is 3, and now we got to find the x values. Well, you probably know what they are just because you know absolute value, but let's just review our calculator here. So we do second calc, and we'll go down, we'll get the first one. We're going to say, where does this intersect? So if you just put the cursor somewhere near the intersection point, anywhere, then you hit enter 3 times. This is the fun one to do because it's really no work. 1, 2, 3. And there's your first answer, -3. So we know the other one's going to be +3. So x equals -3 and x equals +3. And we have 2 numbers for our solution to the absolute value. Okay, so when you have an absolute value of x equal to 3, similar to our quadratic, we're going to get 2 answers. We know that if x was +3, then the absolute value of +3 is 3. We also know that if x is its opposite, -3, the absolute value of -3 is 3. So we have 2 solutions. That's the main thing to keep in mind. When you solve an absolute value equation, you're going to have 2 answers. So the moral of the story here, and usually the only problem I see with students doing absolute value equation is, notice I do this little branching off idea to remind me that I have to set this equation equal to 2. Minute you branch off like that, drop the absolute value symbol. Just drop it out of the equation. And what goes on the right and left side here are 3 and its opposite. Okay, 3 and its opposite. So, oops, I didn't mean to do that. So if you want to have sort of a generalized idea of how to solve any absolute value equation, here it is right here on your paper, all right? If C is a positive real number and U represents any algebraic expression, any, notice in this particular case, the algebraic expression was simply X. That's all that's in between those, but it could be any expression inside, anything. Then to solve the absolute value of the stuff inside, which we call U, equal to C, then you create two equations. You drop the absolute value and you say U is either equal to C or U is equal to its opposite, which is in this case, I know is a negative number because look at how C is defined. C is defined to be positive. So when I see dash C, I know that's negative. Okay, so the key here is getting rid of those absolute values and creating two equations. So let's try one of these. All right, so here's an absolute value equation. And so the first thing we want to do is to rewrite the equation without absolute value symbols into two equations. One equation is going to be equal to positive 11 and one equation is equal to negative. So you want to take the stuff inside, let's call that the stuff, and set the stuff equal to 11 and the stuff equal to negative 11. Once you do that, you're all done. You just replace the stuff with 2x plus 1 is 11 and 2x plus 1 equals negative 11. And now these are two baby linear equations. You're all set to solve them. You subtract 1 from each side. 2x equals 10. X is 5. God, life is beautiful when they're this nice and easy. Subtract 1 from both sides. 2x equals negative 12. X equals negative 6. Oh, 2x. 2x plus 1 is, don't you have it right there on your paper? Oh, you don't have your lecture notes with you today, either one of you. Oh, okay. Yeah. They were handed out a while ago, Summer, and you haven't had yours for a while. So 2x plus 1 equals 11. Okay, so you take this, 2x plus 1, you set it equal to 11. And let me just say, I think I mentioned this last time, Mason, they're all online. Okay, all your lecture notes are online. So you can copy them out on your own. 2x plus 1 equals negative 11. They're under lecture notes for test 1 in Moodle. So let's check this equation. Let's check 5. Go back and put 5 in where you see x. You get the absolute value of 11 is 11 and you're happy. Then you put in a negative 6. And you get negative 12 plus 1, which is negative 11. And the absolute value of negative 11 is 11 and you're happy. Okay, it all works. Did you have your hand up, Chris? Oh, I saw it partly up. Oh, okay. Do you want to tell me what was a little? The absolute value sign, the point of it, Chris, that's a good question, is because if I didn't have the absolute value there, I'd only have one solution because I'd be solving for 2x plus 1 is 11. But because I have absolute value, I know that the number inside could be a positive 11, which is what you're saying here, or a negative, and that's what gives you your two answers. Okay? Anything else about absolute value? Okay. I'm a little curious here about if I'm going to be able to do this next part with you without not the equations, but the inequalities. I mean the number lines, because all my number lines didn't come off on here. I don't know why. Let me show you the only error that I've seen in all the years I'm teaching. The only student error that I've seen with these absolute values. So this is what sometimes I see students do with these. That's incorrect. They go like this. They don't remove the absolute value and they start solving it like this. And then they get one answer. Okay? They end up getting an answer that works when you set the whole thing equal to 11. But notice you can't pull that out because the thing inside is the opposite of, you can also write it like this. Here's another way some of you may have been taught to do these problems. You might say that 2x plus 1 is 11, or the opposite of 2x plus 1 is 11. The opposite of what's inside. So if what's inside is negative and you take its opposite, you're going to get 11. This tends to be a harder way for you to see it, but I've seen some students solve it this way. So notice this equation is exactly the same as what we got right here. But if you say the opposite of what's inside is 11, then you have 2x minus 1 is 11. And that's why you can't be treating this original equation as a linear equation, because it has the by just subtracting 1 from both sides, because you'll only get, number one, you'll only get one answer, which will be correct, but you're going to miss the other answer, because the other possibility for what's inside here is negative 2x minus 1, the opposite of 2x plus 1. So that's the one error that I've seen students do. So remember, before you start working the solutions to the equation, drop the absolute value sign, make one side 11 and the other side negative 11. Chris?
How do you make what is this that you solve for? That kind of defeats the purpose of that.
Okay, so this goes back, were you here the first day of class when we talked about the definition of absolute value? So remember, we had this definition if x is positive and or equal to 0, and this one if x is negative, right? So the idea here is to say, what could be in between those? What would be true? Let's forget about solving the equation right now. What could I put in between those absolute value symbols right now? So this would be true and that would be true. Don't even think about that. What could I put in there? What number could I put in there? Negative 11 or positive 11. So all we're saying is, let me find the value of x that will make that thing equal negative 11. So when I go back and put it back into the absolute value, it comes out being positive. And then the second thing is, what will make it equal to 11? So that's why you set one equal to 11 and one equal to negative 11. Okay? Thanks for asking. Yeah. No. No, C is the result here. This is C.
What if it is?
Because an absolute value could never be negative. So that's why this here says C is positive, because when you start off with this equation written like this, C must be positive if you're going to write U equals C and U equals negative C. Okay? All right. So those are absolute values. Why don't you try this one? Now, again, we're going to follow the same idea. Isolate the absolute value. You want to manipulate this until you just have this on the left side all by itself. So that's the first thing you got to do, is isolate absolute value before you then try to solve it. So you're going to have two steps. It's going to take you 2 steps to isolate the absolute value. Who's missing today? Oh, Sam. Okay. We got for solutions, and if everybody's okay with them, we'll just move on. Anybody want to say what you got for the solution to this absolute value equation? Yep, Paul? 4 and negative 3. How are we with the rest of you on those two solutions? Sounds good, everybody? Okay, perfect. Well, let's move on. So this is again, this will not be, you will not be responsible for this until quiz 2, which is a way away. So this would have been on your test if we didn't have the snow day. All right, so find a neighbor and discuss why this particular absolute value equation has no solutions. If you were to put in the solution for this on my math lab, you would choose that symbol which says empty set. There's no solution. Okay, so discuss with a neighbor or two why this is. Okay. Okay, so let's see, we've had some discussion from this table quite a bit today and over here. And Caitlin, you wanted to say something earlier. Would you like to talk about this one at all? If not, you can pass. Yeah. Right. This is an impossible thing. An absolute value of x, whatever x is, it has to be positive 2 in the end once you've taken its absolute value. So this has no solution. Or again, you could say empty set. Okay. All right, so let's take a look at solving linear inequalities. And for some reason, this didn't come out nice for me. So I'm going to just keep going back and forth from my notes. You have this looking really nice on. Oops, it didn't copy it, did it? Oh, paste. Oh, not that. All right, let's try that again. All right, so let's go back to my Word document. I don't know, this has never happened before. Let's copy that. Let's go back here and copy this, paste. Yeah, thank you. So there we go. All right, so I want to make it a little bit smaller. I'm going to have to do this throughout you'll have to be patient with me. So here we go. So how would we represent the solution to this linear inequality? This is called a linear inequality. We're going to look at quadratics at some point because x is to the first power. How would I write the solution set for this? X less than or equal to 7. X less than or equal to 7. That is a solution set. In other words, if I wrote it in set builder notation, it would look like this. If I use set builder notation. But how would I represent that solution set on a real number line? Summer? Close circle at 7, yep, because I'm including 7, yep. Right, narrow all the way to the left, right. So that's how I would represent this set, the set of all numbers less than or equal to 7. That's using a number line, okay? Now, we can't be going all the time using number lines every time we want to represent a solution set. And most of you have already shown me that you don't particularly like set builder notation. So on the first quiz, I saw that. So the good news is we've got another way to write these sets that are infinite, right? These sets have an infinite solution to them. And it's called interval notation. And this is how we represent, with interval notation, this picture and this solutions, this set. This says exactly the same thing. So let me explain to you how we use interval notation. The interval notation always has your smaller number first. If you are including, and this would be your largest number here, if you're including it, look at this thing. Doesn't that remind you of a staple and a staple gun, right? It's just, so the way I think about it is like when you put that closed circle on your number line, you're including that number, you're stapling that number. You're definitely including that. You're attaching that. Like when you attach something to a paper, you use a staple. If you go all the way to the left, there's no end. All right, so if I go all the way to the left, there's no end. Negative infinity is a concept, it's not a number. So you can't include it. That's why you have the parentheses, because that says I can't include negative infinity, it's not a number. So this interval notation says exactly the same thing as this picture and this set. Yeah, Chris? Okay, what happens? So that's a good question. Suppose we had this. X suppose we had this solution. So we have a what if question. What if? Well, would the left-hand side of our interval notation change at all? No, we're still going out to negative infinity. Nope, because there's an infinite number of numbers, and this is what I hope by the time you leave Math 107, you don't think the numbers in our system are made up of integers. There's an infinite number of numbers right between those two things, 7 and 6, okay? So what do I do if I'm not going to staple 7? I put the 7 there, but what do I do? Parentheses, exactly. What would I do on the number line? Someone told us before you would put a closed circle there. What if I represented this on the number line? What would I do? Open circle. I'm open, I'm not including 7. Well, actually, you're kind of closed in a way if you're not including something. No, didn't say that. All right. So this is interval notation. You're going to use it for the whole remainder of the semester, and it's a lot easier to use and to write than Set Builder and to draw these number lines. So we'll have a little bit of practice with this. Okay, so let's take a look at the next thing. All right, so I've got to go back to my notes here and copy each of these things again. Copy. Oh, you're right, I could, thank you. Yeah, I could have, thank you. Oh yeah, maybe I should have. All right, so here's something in interval notation. What you got to be careful of is when they're both parentheses is not to see it as a point on a line, because it will be representing a set of numbers, which will always be an infinite set, okay? So this is an example of what we call a closed interval. And if we were to write this in Set Builder notation, this is what it would look like. I want all the numbers between 2 and 3, and there's a zillion of them, right, Summer? Including 2 and 3. So on my number line, I would put a closed circle at 2 and a closed circle at 3, and I'd put a big fat bar in between them. That's what it would look like on the number line. This is what it looks like with interval notation. And I have the staples on either end because I'm including both numbers. So they both get stapled together. All right. Now let's, I want to get a copy of this. Oh, I've already, I should have copied it before I worked on it. Okay. Let me make a couple copies of these so I have them in reserve for when I might need them. All right, so let's go down to the next one. All right, so this is an example of an open interval. Notice they both have parentheses, and that means I'm going to be some number between -1 and 5, but -1 and 5 don't get entrance into my club, into my solution set. So I put an open circle at -1 and, whoops, let's go up here, an open circle at -1 and an open circle at 5, and I color everything in between. Okay. So why don't you try the next one? You try the next one at your seats. Okay, someone want to tell me how we would represent this particular interval on a number line? How about you, Bob? I haven't heard from you today. An open circle at -4, close one at 1, and a line in between. Is everybody all set with that one? All right. Now, these last two intervals are examples of infinite intervals. And again, parentheses are always used around negative infinity and positive infinity. So anytime you're using negative and positive infinity, you use a parenthesis. Okay? All right, so these are useful when we have to solve linear inequalities. That's why we are bringing this notation in now. So let me continue to move along here with this. I'm going to just borrow these again. And oh no, I already had it copied, right? Time. So here's the number line. Let me copy this again. Put it over here. All right, so there we go. All right, so linear inequalities. I think most of you, I'm pretty sure most of you are familiar with linear inequalities. You've solved them somewhere along the way. And the only thing you have to remember about linear inequalities that makes it different than solving a linear equation is, number one, your solution set isn't going to be a single number. It's going to be a whole set of numbers, infinite set of numbers. And the other thing is you have one rule to remember that makes it different than solving a linear equation. And that is anytime you multiply or divide both sides by a negative number, you must reverse the direction of your inequality symbol. That's the only thing you have to remember. So if you notice the very first equation the very first inequality I have here, you're going to be subtracting 3 from both sides and dividing by 3. Absolutely no problem, nothing to worry about. So here you subtract 3 from both sides because you're isolating the variable just like you've always done. You divide both sides by 3 and you get the inequality x is greater than or equal to -1. So on the number line, it looks like this. In set builder notation, it looks like this. You just throw in the inequality right there beside x with that vertical line. And then interval notation, which is a brand new interval notation idea. What would I do for interval notation? How would I represent it in interval notation? Anybody at all? I have a staple, a closed bracket. Yep. Yep, the full thing. So you want to start, all right. So Tony's starting with the bracket. Who else wants to help? Yeah, Mason? -1, comma. And where do we stop? Never. So what goes here? What direction are we going in? Right, so it's positive infinity, and then how do I finish my interval off? Parenthesis, right. So now with this one, because I'm dividing both sides by -4, I get x on this side, I get -2 on this side, but this thing reverses direction. So now I'm looking at the set of numbers bigger than -2, but not including -2. So in set builder notation, that looks just like this. And in interval notation, how would I write this? Elena, can you help me? Absolutely. Very good. Yep. Okay. So that's it. All right. Let's see if we have anything else cooking today. Ooh, do we want to go? This is I got to get through this with you. Okay. So, do I have a group activity at the end of this one? I think this is just a long lecture.
Yes.
I do? Okay, good. So, I want to do one of these for you, and then I want you to spend some time with that group activity because it will help you. The following inequalities can be combined into a single inequality called a compound. It's like a compound sentence. I got the call that GCC was canceled on Friday, and I went back to bed. You know, something where you put 2 full sentences together. That's what this is. Any ideas how we can combine these 2 inequalities into one? No, we're going to make them into one. Okay. No, what do they have in common? What's the x minus 4? And x minus 4, and then what do I put on either side of it? How could I represent this with just 1x minus 4? Right, -6 less than x minus 4, and x minus 4 less than or equal to 1. So to solve a compound inequality, we're going to use the interval notation to represent the solution set. Here's how you can do it, folks. You can treat it as 2 separate inequalities like we have right here. Solve each one of these if you want. So you could just do each one of these separately, or you could do it all at once. Efficiency. You could add 4 to both sides. So you don't have to worry about changing any direction because you're adding. So we get -2 on this side is less than x, which is less than, which is less than 5. Okay? So I just added 4 to both sides of that inequality, and there's my solution set looking at you right in the nose, right? It's going to hit you. This is the solution, yeah? So how do we use interval notation to represent that solution set? Open parentheses, -2, comma, 5, close bracket, right? Like staple. All right, so to use your graphing calculators, we'll save that for another day. It's not as important as learning how to solve these. So what I'd like you to do now is I'd like you to start working on the group activity.